Hello, my name is Geert van der Snikt. I'm a cultural heritage scientist and I work for the University of Antwerp. I'm presenting here a lecture that I gave during a conference on Hans Memling that took place on the 13th of March 2017. This symposium was organized to celebrate the completion of the conservation treatment of Hans Memling's Christ with Singing and Music Making Angels, a late 15th and large triptych that is part of the collection of the Royal Museum of Antwerp. Other speakers of the conference talked about the many new insights that were obtained during the conservation process. A number of the more technical findings concerning the painting technique, the materials used, and their degradation were gained by means of analytical techniques. I would like to tell you something more on the research methodology that was used to obtain all of these results, and more in particular, I would like to discuss how this research methodology evolved and expanded in the course of this lengthy conservation process. The conservation treatment of the vast panels took off in 2001 and was completed in 2017. That is quite a long time. During that period, conservator Lisette Claassen and her colleagues kept working on the panels with great persistence. And that in between running a very lively conservation studio, which you see here, and moving an entire museum collection. During those 16 years, many new things entered our daily life, making it more easy or even more complicated. I'll let you decide. So the world and especially technology around us experienced a strong evolution, and the same thing can be said for the technology used in cultural heritage science. Therefore, I would like to explain how the research methodology changed in that period and how the Memling panels and the Antwerp Museum in general played a role in that progress. When preparing this talk, I digged through my old computer files and I found this early picture from 2005. That was my first encounter with the panels, right at the start of my PhD, so at the kickoff of my career. So you could say I have a personal connection with the panels. My promoter Koen Janssens had seen the panels at that time and thought it was a good idea to do something with the panels. And that something became quite a lot over the years, because every time a new instrument or new technology became available, we returned to the museum where God and His angels received us time and time again. Over the centuries, the painting suffered from discoloration, and when you look very careful to this old picture, you might notice that also my hair suffered from discoloration. So that's another personal connection I have with the panels. The first research we performed on the panels was with the portable X-ray fluorescence spectrometer, a MA-XRF. And today, in 2017, MA-XRF instruments have become mainstream instruments. Most research institutions and also large museums with an own scientific department have such an instrument. You can buy them from many different companies and they come in different designs. But in 2005, this MA-XRF was a novelty, and the handheld instruments were therefore the forerunner of what I like to call a first revolution in heritage science. Let me explain this a bit further. When you want to look inside a painting, you have to perform technical research, and this can be done either non-invasively, directly on the painting, or invasively, and that's then on paint samples that you take to a laboratory. Until the turn of the millennium, non-invasive research was mainly performed with traditional imaging techniques like X-ray radiography or infrared reflectography. The great advantage of these diagnostic methods is that they are mobile and that the result is an image and thus relatively easy to interpret, although you still need quite some connoisseurship and expertise to really understand what is happening. From the 60s and 70s onwards, a number of lab-based or stationary techniques were introduced to perform analysis on paint cross-sections. Especially the scanning electron microscope or SEM-EDX became the true working horse of the cultural heritage scientist. You see here the first scanning electron microscope that was installed at the University of Antwerp in the 60s. You can admire it in the entrance hall of our building together with its original operator. Great advantage of these techniques is that you can identify materials, but most results are presented in graphs and spectra that are more challenging to interpret. Also for the Memling panels, SEM-EDX, scanning electron microscope, was fully exploited, and in between all state-of-the-art technical evolutions, it's sometimes forgotten how truly useful, let's say, traditional SEM-EDX is for studying paint samples. I do not have the time to discuss all the samples, I just show you one cross-section. It is taken from an interesting location because it's in an oxalate area, and several paint layers overlap here. The gilding, the light blue feathers, and the green feathers from the wing of the angel are all present in this sample. You can see how the elemental maps supply a clear insight in the very complex layer buildup at this specific location. The scheme on the left summarizes what is found here. A triple preparation layer, a mordant with its gilding, a single layer of the light blue feathers, and a double paint layer for the green feathers. On top of that, a stack of aged, mainly organic layers, probably old varnishes, and finally the disturbing opaque layer that was later identified as calcium oxalate, and which is discussed separately in an article by Lisette Klaassen. So in summary, the great advantage of SEM-EDX is the fact that you can obtain a clear image of the stratigraphy, even when it's very complex, and that you can collect compositional information from each layer in a selective way. So when you select your location wisely, you can obtain a lot of information from just one cross-section. However, there are some limitations to the technique. First of all, it's a destructive technique, as you have to extract a sample from the paint layers. And the sample preparation is somewhat tedious and labor-intensive. This limits the number of samples that can be taken. And also the sample location is determined rather by opportunity and less by necessity, as samples can only be extracted on the edge of an existing paint loss or on the edge of the painting. Also, one could raise the question how representative this information is for the rest of the painting, because you know exactly how this quarter of a square millimeter is composed, but you could say that you are missing the rest of the circa 12 million square millimeters of these panels. It's exactly these three limitations that can be tackled with mobile equipment such as MA-XRF, which you see here. In contrast with SEM-EDX, MA-XRF can be done in situ, it is non-invasive and very quick, so you can perform as much measurements as you like. For the Memling panels, we performed hundreds of such measurements, and this allowed us to extrapolate the results of the cross-section analysis to the entire surface of the panels. An important drawback of MA-XRF is the fact that it's an elemental technique, so you have to combine the colors that you see visually with the elements that you find with MA-XRF to actually deduce which pigment is present, as you can see summarized in the right hand corner. This problem was more or less solved by another research group who understood the potential of mobile equipment in a very early stage, and that's the Italian research group around Professor Bruno Brinetti and Costanza Miliane. They had the bright idea to collect all mobile equipment that is relevant for heritage science, put it in one van and tour Europe with that van. This was turned into a European project called Molap, and this project was very successful and prolonged and expanded under the names Charisma and Hyperion. In 2009, the Molap team accepted our invitation to come to Antwerp, where they filled the entire conservation studio with their mobile equipment. The most informative techniques were mobile X-ray diffraction and reflection FTIR instruments. All these measurements proved very complementary with our previous MA-XRF analysis. I will explain this with two samples. In the middle you see a detail of the paint surface. There is a paint loss where the preparation layers are exposed and thus accessible for analysis. In fact, there is a kind of staircase. In location 1 you can analyze the upper preparation layer, while in location 2 you have access to a lower or a deeper preparation layer under that. However, when you analyze both locations with the MA-XRF, the spectra will tell you that there is calcium. FTIR and X-ray diffraction will tell you that calcium is mainly present as carbonates or chalk in the first location, while sulfates, or in other words gypsum, is the main constituent in the lower layer. A second example is this spot in the oxalate area, where MA-XRF tells us that calcium is present, while X-ray diffraction reveals the presence of weddellite and webellite, two crystal forms of calcium oxalate, and this is then confirmed by FTIR. So in this way, a whole new group could be added to the research methodology, namely the group of mobile analytical techniques. And you see that I left some space in between these two groups, which lets you assume that yet another new invasive group was added to our methodology. And that's the group of instruments that perform so-called chemical imaging. I put this group in between imaging techniques and mobile analytical techniques, and that's not a coincidence, because this group combines the advantages of the other two groups and at the same time neutralizes their drawbacks. Chemical imaging is non-destructive, it is performed in situ, and it is able to identify materials, and the results are presented in the form of an image, not an enigmatic spectrum. How does this work, this chemical imaging? Well, since 2008, our group in Antwerp has been transforming the existing mobile analytical instruments into scanning versions. Our first scanner, which is more or less famous now, was the macro X-ray fluorescence scanner, and basically that is a MA-XRF instrument turned into a scanner device. So instead of performing a few hundred measurements in selected points, the scanner performs millions of measurements covering the entire surface. Also, mobile FTIR instruments that you saw earlier were transformed into a mobile scanner, which you see here. And finally, X-ray diffraction was also turned into a scanner by my colleague Frederik van Meert. What do the results look like for Memling? Well, for macro-XRF, instead of these MA-XRF spectra, you obtain a set of distribution maps. And each map tells you how a specific chemical element is distributed over the paint surface, as in this detail of the angel. When you combine this with FTIR or X-ray diffraction scanning, you can also learn in which form these elements are present. For instance, here you see the map of calcium in the XRF scanner, but the FTIR will tell you if it is present as chalk or gypsum or even oxalate, which is not in the list here. This visual aspect is especially important in a time that conservators have to give account for their choices for intervention, not only to fellow conservators, but also international steering committees and through social media. As such, you can consider these images as objective scientific arguments that conservators can use to underpin their choices in an unbiased way. My story is not finished yet, because there's even a third revolution, and that's the revolution of, or the introduction of, synchrotron radiation-based analysis. Whereas mobile equipment and chemical imaging brings the chemistry to the museum gallery, synchrotron analysis is again performed on samples in large and remote facilities, such as this one. That's the ESRF in Grenoble. This type of analysis is particularly useful to unravel the particular complex chemical degradation pathways of degrading and discoloring painting materials. I do not have the time today to go deeper into this, but I can illustrate its usefulness just by showing a selection of papers that we recently published on recent breakthroughs in the understanding of pigment degradation. and that's all thanks to synchrotron radiation. Let us see how this works for the Memling panels. I will show you one example. This sample was taken here in the feathers of an angel that is in a red lake area. This is the cross-section, and this is, let's say, the schematic layer buildup. You have a double preparation layer, an underdrawing, a mordant with gilding, and on top of that two red lake paint layers. One is opaque and another more transparent. On top of that there is a thin oxalate layer. On the left you see how SEM-EDX again gives us a nice overview of the sample and the layers and the elemental distribution. On the right you see the results of synchrotron radiation micro X-ray diffraction imaging experiment. You perform this typically on a small area of interest on the sample, and then you obtain high resolution species selective information. The results can be summarized in these colorful and intuitive distribution maps. Micro X-ray diffraction identifies the crystals, in particular a layer of gypsum shown in white, followed by a layer of calcite, so that's chalk, shown in warm yellow. Then in green there is hydroxyl apatite, which is bone black from the underdrawing in normal English. Then some goethite or yellow ochre in the mordant, indicated in yellow. And the gold from the gilding shown in blue. And then we come to the double red lake paint layer. You can see that they are completely different in composition. The first one is full of hydroceresite or lead white grains, that's shown in red, making it more opaque, while the top transparent lake layer contains especially anglesite, or in other words lead sulfate. The latter is possibly a reaction product of a lead dryer that was added to the lake. So you see how we can start identifying secondary products thanks to synchrotron radiation. With that I mean products that were added in a certain chemical form in the paint but reacted further in a later stage. And then finally on top there is a thin layer of oxalate. So in summary, we can obtain extremely specific information in very high resolution from a small area with this technique. For the conclusions, I would like to return to the first slide, and I hope that I convinced you that since the beginning of conservation treatment, no less than 3 revolutions took place in cultural heritage. First, the dawn of mobile equipment, then the introduction of synchrotron radiation-based analysis, and finally the birth of in situ chemical imaging. And I hope that I convinced you that the University of Antwerp and the museum and the Memling panels played at least some part in those revolutions. Most of the results that I discussed today were published in 2 papers, and in case you're interested and you cannot access them, you can find them on my account on ResearchGate, so please feel free to visit my account there. Since I have your attention now, I would like to make some publicity for this paper as well, that was just accepted by Angewandte Chemie, a very high impact journal. It's a close collaboration between the KIK IRPA and the University of Antwerp, and it deals with the macro XRF scans performed during the conservation treatment of the Ghent altarpiece by Van Eyck. Next to the Memling panels, I think this is again an excellent example of how an intensive collaboration between chemists, conservators and art historians can lead to breakthroughs in all of these fields. And I thank you for your attention.